Hey, Mr. Harrod, I'm here. We're going to go over the three types of bonds.
Excellent!
Yeah, very excellent to go over the three types of bonds here. So the first type of bonds we have are ionic bonds. Okay, we look for metals and nonmetals, or we look for the polyatomic ammonium and a nonmetal. Okay. There is a list of polyatomic ions in the reference packet that are also referred to as nonmetals by me, so you need to get yourself familiar with those and memorize those. Okay. So what happens here is the metals are losers. Okay. They lose their electrons to the nonmetal here. And nonmetals are the winners of the electrons here. So what happens here from the sodium loses one electron, okay, and the chlorine gains one electron. Notice that they lose and gain the same amount of electrons, ending up with an Na with a plus charge and a Cl with a minus charge. You end up with a cation and an anion, okay? And usually we do not write, if I write this as a compound, I usually do not put the charges in there, okay? This is electron stealing. That is what happens in ionic bonding, okay? Covalent bonding, these are between two nonmetals, okay? And this is electron sharing. Oh, how nice. It's very nice that they share electrons.
All we are is dust in the wind, dude.
Yes, I would agree. Now there is two ways to share. There is unequal sharing, which is called polar covalent, and we'll get into more detail of that later. And there is going to be equal sharing, which is non-polar covalent. Okay. Then we have this metallic bond here where there is a sea of electrons. And they move from metal ion to metal ion. This is what allows metals to conduct electricity. Remember, metals conduct electricity because they have these electrons and they just move around, go woo, wee, woo, wee, wee, and they all just float around the sea and flow and stuff like that. Okay, those are the three types of bonds that we're going to go over. Okay, so we're going to go over ionic bonding first here. Ionic bonding structures. Ionic structures have an alternating positive and negative charges in a rigid lattice. In a rigid crystal structure. It's a rigid solid. Okay. Electrons are transferred. Let me take that watch off. That's annoying me. We need another sound effect, don't we?
No way.
Yes, way. Okay. Transferred from one species to the other. Electrons are transferred from the metal to the nonmetal. Okay? Because remember when we're doing ionic bonds here, you can't see that. We're going to have metals and nonmetals, or we're going to have ammonium and a nonmetal. Ammonium is one of those polyatomic ions. Okay. Okay. Predicting the substance type. Okay. Again, you're looking for metals and nonmetals, or ammonium and nonmetals. Okay, so you're looking for compounds like CaCO2. Calcium's a metal, that is ionic. You can also have it with a polyatomic ion, so Na2CO3. Sodium's a metal, and this is carbonate, that's a polyatomic ion. You can have ammonium chloride, NH4. Ammonium is NH4 plus, so NH4Cl, that would be an ionic compound. And what else can we have here? So we have a polyatomic ion, so NH42 with SO4. That is also an ionic compound because it has ammonium, and that is a polyatomic ion sulfate. Okay, predicting electronegativities by calculations here. Okay. Electronegativity is the pull of an electron to gain an atom. Is one of the most important properties to know. If the electronegativity difference is 1.7 or greater, it is ionic. Okay. Electronegativities, there is a periodic table listed in the reference packet that has these numbers that I am using to do this. Okay, so what you do here is you look up those electronegativities. Maybe I should get one. Let's pause the video for a second.
Strange things are afoot at the Circle K.
They are. Okay, so I have an electronegativity periodic table here. There's one like this in the reference packet for you here. So what you do here is for chlorine. So chlorine has an electronegativity of 3.0. Sodium has an electronegativity of 0.9. You subtract the 2, you get 2.1. So this NaCl is an ionic compound. Okay? Because the difference is greater than 1.7. That's how I know if it's ionic. If it's below 1.7, it is covalent. So for instance here we got iodine. Iodine has an electronegativity of 2.5. You do not need to include the 2 in this calculation. Be would be 1.5. You subtract those 2, you get 1.0. So this is actually, this will be polar covalent. And we'll learn the numbers later, but it's polar covalent, trust me, according to the electronegativity difference. Okay, bromine has an electronegativity of 2.8. Aluminum has an electronegativity of 1.5. So this is going to be 1.3. So according to that, that will also be polar covalent. Okay. And this electronegativity difference scale, it's kind of like the Richter, well, I don't want to say it's like the Richter scale. It's like the scale they use for hurricanes, like category 1, 2, 3, 4, and 5. You know, the higher you go up, the more ionic it is, and the numbers are relatively, because their magnitudes are, they're relatively just numbers, you know. So 1.3 is closer to being ionic than 1.0. Okay, and then the final one here, chlorine. Chlorine has an electronegativity of 3.0. Copper has an electronegativity of 1.9. You subtract those 2, you get 1.1. So that is technically acting polar covalent as well. Okay, based off of the electronegativity differences. Okay, you guys are champions. The legend is